case you haven't guessed, you're at the opening of the Pine Valley Bridge. S.J. Groves and company did finish the bridge. As you know, they were here until 20 minutes ago spraying sand. At least those of you that were here a half hour ago. I think they've left now. They've gone down the freeway and they're busy going down the freeway, up the right way off also. But we do want to welcome you here. We people in Mountain Empire are pretty proud of this area. I know a lot of you are here. We've got a gentleman here. He came up with us. I saw a gentleman here. He was with the Valley Pioneers. And he said he came through this area in 1902 and wanted to know if I was here then. But 450 foot bridge. It really is awesome. And I think you want to recognize here the people that built it. And that is, of course, the California Department of Transportation. We have with us today from Caltrans the Assistant District Director.
A bridge is structural art, the result of man's ability to conceive and to build. But before this final celebration stand months and years of concept, decision, and design based on years of experience.
The Pine Valley Creek Bridge is a segment of Interstate Highway Route 8, which runs between San Diego, California, and Yuma, Arizona. Route 8 in this area is the principal east-west...
Mr. Bert Bizzoni, bridge engineer.
California. In the course of upgrading and realigning the route in this area, it was necessary to cross the deep canyon formed by Pine Valley Creek. The bridge, as it crosses this canyon, is 450 feet above the creek bed. The bridge site is located within the Cleveland National Forest and is some 40 miles east of the community of San Diego. The banks of the creek at the bridge site slope up and away at an approximate angle of 2 to 1. The length across the canyon at roadway grade is about 1,700 feet. The first and obvious question, as the site was reviewed, was why a bridge? Why not fill and culvert?
Our district hydraulics people studied the problem. The culvert idea was rejected for several reasons. First, the need to minimize scarring the landscape within the national forest. Then the high cost and unknown behavior of a fill 450 feet high. Also, fill material in such amounts was not available along this route. Next came the questions of type and span lengths. Basically, 4 types of structure were considered feasible for this site: steel arch, truss, plate girder, and concrete girder. For a stream crossing of this type, an important feature, one that determines the looks of the structure, is the length of the main span. Short spans and many piers give that picket fence appearance. Long spans look good, but are expensive. As a compromise, a center span of 450 feet was selected. The side spans were reduced to the following layout: 270, 340, 450, 380, and 270.
From our studies, the concrete cantilever bridge emerged as one of the most economical and aesthetically acceptable structure types. Cantilever construction is a fairly recent development and has been successfully used to build bridges in other parts of the world.
California's effort is the first bridge to be constructed in the United States using cast-in-place cantilever construction. At this point, one might ask, what is cantilever construction? And why should it be more economical than other types of construction? In the usual construction of a concrete box bridge, the false work is erected first. The concrete is placed in the forms, cured, pre-stressed if necessary. And after false work removal, the structure is completed. In the cantilever method, the structure is built in segments, and each completed segment supports the false work and the forms needed to construct the next segment. The unique characteristic of needing no ground-supported false work for construction makes this method ideal for this use. The bridge is built from the piers outward by using a pair of travelers, one on each side of a pier, from which the forms for the concrete box girder are suspended. In appearance, the various stages resemble a capital T, with the arms getting ever longer. During construction, an automatic time-lapse camera is fastened to the hillside. Taking one frame each 6 minutes during the months of construction has produced a visual history. Each working day will pass in 3½ seconds. A typical sequence of operations is something like this. First day, move the travelers ahead, align vertically and horizontally, and secure in position for the next pour. Second day, place the steel reinforcement post-tensioning ducts, pre-stressed bars, and the interior forms. Third and fourth days, place concrete in the segment and cure it. This is a critical stage because a concrete strength of 3,500 psi is required in 30 to 40 hours. Fifth day, stress the post-tensioning tendons, free the forms, and get the traveler ready to move. Once the cantilevers reach a predetermined length, the travelers are moved to another pier and another pair of cantilevers are constructed. When two cantilevers meet, they are joined to create a continuous span. Mr. Ostap Bender, bridge designer.
The design basically is a trial and error process. A series of sections is assumed at various points 15 feet apart. Deadload moments and moments due to false work, carriage, are then computed. Live load plus impact moments are computed for the completed structure. Moments due to placement of rails are also computed on the completed structure. From these figures, the maximum design moment is determined for each point. Stresses are computed for top and bottom fiber, and finally, the required pre-stressing force, P sub F, is calculated. Once minimum P sub F and E, eccentricity of the tendons, have been determined for each point, the two curves, minimum P sub F and minimum P sub F times E, can be plotted. Now, a required minimum P sub F and P sub F times E for any point may be scaled from the plot. By including this diagram in the plans, the question of segment length and tendon size is left open, achieving maximum flexibility and giving a chance to all major pre-stressing systems to compete for the contract.
For this structure, all concrete was pumped for both piers and boxes. To obtain the required 5,000 psi compressive strength in the concrete at 28 days and 3,500 psi at 8 hours to permit full pre-stressing, the contractor used 8 1/4 sack concrete with a cement of finer grind than usual. The concrete was cured by continuously spraying water on exposed surfaces. During the winter, the forms were covered with a 2-inch insulating layer of styrofoam. The Diwadag 1 1/4 deformed bar pre-stress system was used for all stressing work. The prefabricated 33-foot lengths were placed and spliced as required. The straight lines and plane surfaces of the structure match the uncluttered site, which has few trees and many rock outcroppings. The superstructure consists of parallel boxes, each providing a 40-foot roadway between the railings. The boxes, in addition to being post-tension longitudinally, have transverse stressing in the top slab to allow the use of a thinner section, thus reducing the dead load. One advantage of this method lies in its efficient use of materials. The thickness of the compressive slab and the amount of the pre-stressing steel at any given section are proportioned to resist just the applied loads at that point. The piers are cellular, and despite some curves, are well suited for slip-forming operations. The contractor, however, chose a self-climbing form system using Teflon-coated steel. Structurally, each pier consists of 2 columns tied together at about 90-foot intervals vertically. At the top, the columns flare out to a common cap supporting the 2 parallel boxes. Wide deck overhangs were selected to minimize the apparent depth of the box, and they also contribute to the economy of the overall design. Further advantages are derived from the use of semi-production line techniques in the construction process. Since the bridge is built in segments, a fairly small crew performs repetitive tasks on about a 7-day cycle. Control of materials and workmanship is easier, more thorough, and production rates are greater.
The concrete cantilever method of construction was selected at Pine Valley for a number of reasons. Primarily economic.
Ralph Samariva, resident engineer.
This method has been used extensively in Europe, and with it, a cast-in-place concrete bridge can be constructed without the use of what we refer to as conventional false work. In other words, no ground support is needed to support the freshly placed concrete. Hence, the slopes of the bridge, or the slopes of the valley underneath the bridge, do not have to be disturbed for false work paths or other things. We permit the contractor to use a marginal road system to gain access to the base of the piers, but this road system will have to be regraded and reseeded after completion of the bridge. A structure of this size normally would have required tremendously large footings. With this in mind, and also keeping in mind the slope of the ground where the footings are located, very large benches would have had to have been excavated into the solid granite along these slopes. In lieu of this, the Department of Transportation decided in favor of a pre-stressed rock anchor system, which had the effect of reducing the size of the footings considerably. And the California Department of Transportation is extremely proud of it. And personally, I think it's really something.
The only intrusion into the valley's life, its ecology, was the single-width dirt road. Now even that has been erased and the slopes reseeded. At the bottom of the canyon, the small creek wanders its way, as it always has. The sounds of heavy construction have gone. 130 million pounds of concrete and steel have been placed here to bridge this canyon. And it's left things pretty much as they have always been. are seeing compressed time and a bridge growing into empty space. Each working day is passing in 3½ seconds as sweeping shadows from the sun slide from horizon to horizon. The bridge is in Pine Valley, California, east of San Diego, and it's probably the most unique bridge in the United States. Designed by California's Department of Transportation, the main bridge deck grows outward from each column. The spans stretch section by section into thin air and then are joined together to form the first bridge of its kind in this country. This kind of country has a very delicate kind of ecology. To place 130 million pounds of concrete and steel here and leave things relatively undisturbed was no small accomplishment. Pine Valley Bridge, a new concept.